see, I see we have a small group today, and so I hope what we're going to do is just pause a little more often, and just in case you need anything clarified or want to discuss anything further, we'll have more opportunities for that today. And then, of course, this will be recorded, so please, you can tell your friends about it, find it on YouTube. And I also, just before I forget, I want to remind you that for Minnesotans that are attending, you will get an email with a CEU for your attendance in this webinar today. So let's begin with some introductions. So welcome everyone again. And so you will have two facilitators today. Rebecca is here from Mankato, and then me, Amy. And we're going to talk through inequalities and systems of equations, which is kind of a dense topic, but I think we've got we're able to break it down for you in this through our presentation. And then we also have Amber here, and you've been hearing her voice. She's the tech support today. So if you have any technical questions, she is the one that can help you.
So I just want to remind you, this is Amber, that we have lots of ways for you to participate with us today. We are recording this webinar, so don't forget to come back and check it out on our Minnesota PD YouTube page. We will be using the chat feature quite a bit, so if you look on your control panel on the right side of your screen, there is a chat option. Remember, there is a drop-down thing available, so you can pick a certain person you'd like to talk to, or if you'd like to talk to the whole group. You can find my name. My name is Amber Deleger. If you have any tech questions along the way, I'm here to help. We will also be having everybody on mute, so don't worry if you're trying to talk and we can't hear you. It's because you're on mute. We can unmute you if we need to, but the best way to get our attention is either to chat or raise your hands. Once again, if you have any technical questions during this webinar, go ahead and directly chat them to me.
This is just Rebecca Strom, and I just wanted to also welcome you, and I look forward to visiting with you throughout this webinar.
And like we've talked about, if you have questions about the content of this webinar, please go ahead and chat them, especially with the small group. We should be able to work with questions throughout the webinar. But also, this webinar is structured in an hour as an hour and a half, and so it will be approximately the first hour will be a presentation, and then we'll have some guided practice and even more interactive activities for the last half hour. So that's another time where we can also answer more of your questions. So the objectives for this webinar, again, this is a lot of high-level algebra topics just to cover in an hour, but here's what we're doing. Participants will be able to approach inequalities and systems of equations. So both of these topics are part of the GED test. They are on the college and career readiness standards, and they've come up as a topic of need. And because you may need a refresher yourself on these topics, and because you're going to be having conversations around these topics with your students, we're going to make sure that we talk about them conceptually, graphically, algebraically, and also in context. So hopefully, you know, from approaching these topics from various viewpoints, it won't be a matter of just going through the steps with your students, but you'll really be able to respond to any questions that they have, or you'll be able to approach the questions from different perspectives so that you can reach all of your learners. So that's what we're doing over the next hour and a half. So let's just have you participate right away. So don't worry, I'm not going to call on you, but just please raise your hand if you've recently taught one of these topics. So have you recently taught inequalities, or have you recently taught systems of equations? If so, raise your hand. I just want to see kind of what people are doing. Okay. I see Beverly and Carol have their hands raised. And then some of you are saying no. So, okay, so some of you have recently taught this. So maybe some of these, you'll have something to add to what we're saying, or you'll have some questions that are fresh in your mind. Okay, so because this is part of the Minnesota Professional Development like wider program, I want to just make sure that we're mentioning the College and Career Readiness Standards for Adult Education, what we call the CCRS. So these standards are now available and very easy to find online, and we're incorporating them in Minnesota ABE professional development. And the key shifts with the new standards are focus, coherence, and rigor. And what really came to my mind in the planning of this webinar is coherence. By the time your students are doing these complex algebraic, they're working with these complex algebraic topics, they really need to have a foundation in algebraic thinking, in the skills of solving equations and skills of graphing. So I think this particular episode has a lot to do with coherence. We're building on what your students already know. And then just to look into the actual standards themselves, in planning for this webinar, Rebecca and I noticed that the topics of systems of equations and inequalities were listed in several places throughout the College and Career Readiness Standards. And so I just wanted to, share a couple of these highlights that kind of got my attention. For example, what is jumping out at me right now, the idea of looking at these in the context of real world situations. And one that's particularly interesting, the idea of writing an equality to represent a constraint or a condition. So you're describing a situation. So those are just some highlights of where these topics show up in the CCRS. And then another very useful component of the CCRS are, of course, the mathematical practices. So these are what your students can engage in your classroom in order to become more numerate and stronger with numeracy. And for this particular webinar, one of the practice that really got my attention is to this reason abstractly and quantitatively, mathematical practice number 2. If you read about that practice, you'll see that it's about being able to contextualize and then decontextualize the math. So that it's the idea that your students would be able to think abstractly and then go back into the real life situation and go back and forth between the abstract and then the real life situation. So we'll be focusing on that today. So let's get started with inequalities.
Thank you, Amy. Okay, so we're going to start looking at inequalities today. And with all the CCRS and the GED 2014, there's a lot of information out there. And if you've probably seen this form before, we're going to take some of it. Some of it we're considering prior knowledge. So being able to solve linear one-variable equations, we're considering prior knowledge for today's webinar. But we're going to focus on the one-variable linear inequalities and how to solve them. So thinking about our students, and one thing that they can stumble on a little bit is the definition of an equal sign. They often can think of it as meaning the answer is, and not understanding the idea of two equal values that may not look the same, but have the same value. And this idea of a balance and keeping the same thing on both sides. And so today, it's going to come up quite a bit today. It's this idea of equal sign being where one value may not look like the another value, but we can use one to replace it or rewrite it. So this idea of value is going to be important. And once we can really understand equal sign, then this idea of an inequality can become a lot more clear. So it's this idea now that instead of everything being the same on both sides, one side may or may not be larger than the other. So our basic inequalities are less than or greater than or not equal to, or even a combination of greater than or equal to. We have a situation where things may not be exactly the same, but occasionally they can have an equality to them. So like we mentioned before, we want to look at things graphically, conceptually, and algebraically as we explore these inequalities so that our students can see that it's more than a worksheet, but that we use this in life as well. So this is what it looks like, so let's explore. So if we look at this inequality, we see x is greater than or equal to 1. So let's put this graphically up here. We need to understand exactly what that symbol means. So it is greater than, or it could be equal to 1. So let's start with equality. We're going to find this idea of it could be 1 or it could be bigger. So there's 1 on the number line, but it could also be 1 1/4 or 2 1/2 or 7 or any number of values that are larger than 1. And we end up with multiple solutions and possibly infinite solutions, which the more we fill in these dots, it actually becomes a line. So we're graphing that. The part that our students sometimes don't understand is that this line represents an infinite number of solutions to our inequality. So if we have a different inequality, here's one, x is less than 5, here we're going to have a different situation because we do not have 5 as a possible solution. It can be up to, but not including 5. So if we think of that conceptually, we're looking at all numbers less than 5, but they could be close to 5, 4.9, 4.8, 4 3/4, all the way down. So because 5 is not a possible answer, but super close to 5 is, we have an open circle. That way we're picturing in our minds that the dot is on 4.99, but not itself on 5. And as we're filling in all other possible solutions, we end up filling in, once again, this infinite number of solutions, creating a line. And so we're trying to find this balance of this being multiple solutions. So if we want to compare these equations versus inequalities, the equation, like we said, has an equal sign where both values are the same. Everything on the left has the same value as everything on the right. And when we solve them, there is exactly one solution. For example, x equals 6 has a solid dot on 6. It's exactly 6, no more, no less. When we explore this inequality, we want them to see that one side can be larger than the other, and so we can have many to infinite solutions depending on our situation. So where x is greater than 6, that means that the solution could be any number larger than 6 but not including 6. So we're going to have that open circle and all possible numbers to the right. When we have something like this one, x is less than or equal to 6, it means the solution could be the number 6 or any number smaller. So it can be 6, so we're going to have a closed circle including it and all possible numbers to the left. So as we're trying to help our students visualize what's happening, we want them to see not just the symbols but also the meaning behind them. So let's just do a quick check. So when we have this inequality, I want you to use your chat box to write the answer A, B, or C as the best solution for the inequality. I see an A. Are there any other ideas? I know the boxes are hard to click on sometimes. So as we read this, there we go, now they're coming in. We have the inequality x is greater than -5. And because it's greater than and equal to is not an option here, that is correct, that the answer, oops, seems to be, there we go, is A, because we have an open circle on 5 and everything to the right. All right, so let's review for a minute as we're solving inequalities. We're going to use that prior knowledge of solving an equation. when we solve an equation, we have that strategy of isolating our variable, getting that variable all by itself. And our process is to find out what's happening. Are we multiplying or are we subtracting? And then having to undo it. So when I see it in algebra, it looks something like this. We have the x and we're multiplying by -5, and then we're adding 3. So the first thing we want to do is undo the addition of 3. So we're going to subtract 3 from both sides. We simplify and we get -5x is equal to 25. So now we have to undo the multiplication of -5. So we're going to divide both sides by -5, and we're going to get x equals 5. So how does that reasoning apply when we're solving inequalities? Let's quick review the number line, and we want to look at the positives and negatives. So let's look at our numbers 2 and 8. I have an inequality here that 2 is less than 8. So if we examine those values on the number line, we can compare any two numbers on a number line, and the number on the left is always less. So we can see that it is true 2 is less than 8. So if I want to compare the negatives of each of these, I'm going to notice that -8 and -2 have reversed their order. -8 is now on the left, -2 is on the right, and -8 is less than -2. So we're exploring this idea of crossing that 0 and the order being the opposite, the direction of our numbers increase in opposite ways. So that brings us to these rules of inequalities. We remember some of these rules. When we multiply or divide by an inequality by a negative number, we have to flip our sign. But oftentimes we have a rule and we can't remember why, or depending, when we went to college and school, some of us were never taught why and we had to explore it. So we're going to explore it today, and we're going to play with this idea. Something I've been working more and more in my classroom is this idea of playing with your math. We talk about the idea of people who are truly skilled at something got there by playing. So, for example, if you picture your soccer player, he's the one who did the drills with the coach, but then went home and played in the backyard and kicked sideways and wondered what would happen if I did this. And the same thing happens with somebody who's driving their car. You memorize the book, but you still have to play with the way you turn your wheel. Or when you get a new cell phone, the only way to really learn it is to play with things and discover, hey, if I hold my finger down longer than I expected, this pops up, and now I'm learning more and more, and I'm being much more effective using my phone. So let's play with this idea of why we flip the sign and win. So here we have an inequality. 2 is less than 8. And if I look at my dots on the number line, I can see 2 is to the left of 8, so I know that it is less. If I decide to multiply both sides by 2, because it's an inequality, I'm treating both sides the same, I get the values 1 and 4. So if I look at those on the number line, I can see that 1 is to the left of 4, so 1 is less than 4. So dividing by a positive number, my statement still held true. So let's try this again. So I'm going to start with my 2 and my 8 again and see what happens when I divide by a negative. So if I divide both sides by negative, I end up with -1 and -4. So let me look at these values. What would happen if I kept my symbol the same direction? I'm going to look at my -1 and my -4 and notice that my -4 is on the left. So my statement is now false. So I need to flip my sign to make it a true statement. When I divided by a negative, I flipped to the other side of the number line. Let's try it with multiplying. If I multiply both sides by a -1, I'm going to get -2 and -8. And if I look at those, let's pretend I can hold my sign for a minute, my symbol. If I compare those two on the number line, I'll notice that -8 is indeed less than -2. So once again, by simply copying my symbol, I have created a false statement. So I need to reverse my sign to keep it true, because by multiplying by a negative, I have flipped to the other side of the number line. So now we've at least explored with why it's working and why we need to flip our sign. Once again, these are those rules that we were taught, but we didn't always have the understanding, and our students as adults sometimes need to be able to see what's happening. So let's use this idea and solve an inequality. So just like an equation, we're going to have the same strategy. We need to isolate our variable. We need to find out the operations and undo things, but we're going to be very watchful of that multiplying and dividing by negatives. So if I want to solve this inequality, the first thing I want to do is subtract 8 from both sides. I end up with 2x is less than 12. To undo my multiplication, I want to divide both sides by 2. I'm noticing I'm not doing anything with negatives yet, so my x is less than 6. So I did not need to flip my sign because I divided both sides by a positive number. So as I graph this, use your chat boxes. Do I need an open circle or a closed circle? Exactly. Seeing a lot of open circles. X is equal to 6 is not a possibility here. So because it's not equal, I need to have an open circle, and less than is everything to the left. So let's try one more. Here I've got another inequality. I'm going to isolate my variable. To start, I need to subtract 8 from both sides. I end up with negative 3x is less than 12. I need to divide both sides by 3. And that caught my attention because I know I want to be careful of that, so I'm going to flip my sign because I did divide by a negative. Once again, if we graph this, do we want an open circle or a closed circle? Right, here equal to is an option, so it's a possibility. We need to have x is greater than negative 4, an open circle, and greater than is going to go to the right. So take a quick moment. Has anyone had exercises like this in your classroom where students stumbled with things or things that you found that helped out as well? What are some things that you tried? Or since we have a small group, we can take a quick moment to share some ideas. Okay, maybe we'll share later. All right, so let's move on to systems of equations.
Rebecca,
Yes.
something just because I've been thinking a lot about language lately, just that language of open circle and closed circle, I could see where that would even need explaining. Like it just occurred to me that we just use that and I know exactly what you're talking about but that's just because I'm used to it. But I'm thinking if this is a totally new topic for a student, that even just being careful about how we use language and making sure to say, by closed circle, this is what we mean. By open circle, this is what we mean.
Yep. And
Go ahead.
I was going to say, the idea I like for my students have seemed to work is when we actually draw the inequality and put all the dots on and show that we want to get infinitely close to the number but not touch it. So that's how we kind of demonstrate by playing, but maybe other people have tried different things. Oh, I have not, Andy, I see you said to test which side works. That's true. Make them prove the answer.
Okay, are there any other thoughts or questions before we move on to working with systems of equations? Okay, we'll practice everything in the guided practice at the end. So let's, moving on to systems of equations. Okay, so I just want to start with a very broad conceptual kind of big picture look at what's going on. So as your students are working on systems of equations, there are some ideas that they should be familiar with already. So just the very basic idea that if you have an equation, maybe an equation in the y equals mx plus b form, or just an equation with two variables, that an equation makes a line, right? So that should be something that they're familiar with. And then with systems of equations, though, the idea is that we're not just working with the solutions that are demonstrated by one line, but that we have a second equation and we are incorporating the solutions that are also then on that second line. And so by system of equations, it just means that we're working with more than one equation to describe what's going on. And there also, there can be systems with more than two equations, but at the ABE level, I haven't seen it ever beyond two equations. So that's where we'll work today. So a system of equation is just the two equations. And if you were here, if you saw the scrolling PowerPoint as people were signing in, you may have seen a little bit about this. But if there are two equations, meaning two lines, and you graph them, then a couple different things could happen. So those two lines could be parallel to each other. And so if they're parallel, they're never crossing, and that means that there's no solution that would work for both of them. There's no XY pair that would be a solution for both of these lines. Sometimes one line is right on top of the other line, and that means then that all the solutions are shared. Any point on equation 1 would also be a point on equation 2. And then the third thing that could happen is that the two lines will cross, and I think that is what is most commonly seen in math books. And that's what we're going to work with today. And so what we're interested in the solution to the two equations, we're interested in that place where the lines cross. And because what that means is that coordinate is a solution, in this case for the green line, and then also for that orange line. Okay, so just to give you all a chance to participate here, if the scale of this graph is just 1 unit, one square is 1 unit, what is the solution? What is the solution to the systems of equations? Thank you, Beverly. Good. So Connie is saying the solution is where they meet, and Beverly is telling me specifically what that is. It's a -5, -1 in this situation, and that I thought the same thing. So I just want to, and thanks everyone else for participating too. I just want to take a minute and say, as you're approaching systems of equations, this activity right here, this question I just asked you, would be something that would be quite appropriate at a pretty low level. As soon as your students are able to identify a point on the coordinate grid, they could identify the intersection. And so I'm just reminding you that they don't have to be doing all of the high-level algebra to begin to be introduced to this topic. Okay, so now what we're going to do is take this one word problem, and we're going to process it over and over again. We're going to solve this actually by using a system of equations, and then we will work with those equations in 3 different ways, so you can see all the ways that you could approach this. So I'm going to just read the prompt to get us started. So a GED math class decided to raise money to donate to a summer youth program. They raised $500, 80 bills in all. If the money is a combination of $5 and $10 bills, how many of each do they have? So this is kind of I would call this like a classic 2 variables and 2 equations word problem. So there's the problem again, just so we can refer to it. And now I think where I really want to spend time is how do you even start to talk to your students about this? How do you, what is the conversation that's happening in class? Because that's what they're going to have to do, right? They're taking a test. They're going to have to start to make sense of this all on their own eventually without your help. So let's begin by defining variables. So please chat type in the chat box. What do we need to find? And there can always be maybe slightly different language for talking about this, but there's something that this question is asking us for. So could you all type, what are we trying to find here? Just go ahead and type it in the chat box. Yeah, so there are several ways to approach this, and it doesn't have to be with the systems of equations. You could try different methods, and that would be interesting in itself. But we're going to use this as we're going to solve this with systems of equations. And thank you for typing in the chat box. What we're looking for is we need to find the number of $5 and $10 bills, right? That's what it's asking us for. And so since I'm comfortable with algebraic thinking, I know that it's very common to define a variable for what I need to find. So I'm just going to say let F equal the number of $5 bills and let T equal the number of $10 bills. So then as we talk about those quantities throughout our problem-solving process, we have a variable to represent them. Okay, so now we know what we're trying to find, and what we need to do is take all that information and organize it in some useful way into equations because of what I know about algebraic thinking. Then if I have an equation, then I can solve it. And so the way that I think of approaching this is, what are the two sets of information? I think a very common mistake would be for students to just try to squeeze all that information into one equation right away. And that totally makes sense with how we teach, right? You try to make sense of what's given. But this is actually two equations. So this is a skill you'll have to practice with your students. So what are the two sets of information? And then the way that I am thinking about this is some of this information is talking about the number of bills. So that's like 80, right? 80 bills in all. And then some of the information is talking about the value of the bills. So I see some numbers with value. I see, that $10 bills and $5 bills, that's about value, and that $500 in all, that's about the value. So if we organize these two sets separately, then let's continue with this number of bills. So how many bills? Let's make an equation. How many bills in all? Well, I know there are 80, and I know it's only 5s and 10s, or F's and T's in this situation. So here's my first equation, F plus T equals 80. And then as you do this in your classes, of course, someone could very appropriately say that T plus F equals 80, and then that opens up the opportunity to talk about how that also is correct and why that's okay. And then, thank you. Then I see some of you are also chatting the second equation. So we've worked out how many bills. Now let's work with the value of the bills. So what's the equation for what is the value of the bills? And so we have 5F plus 10T equals 500. So 5F, if every F is worth 5, then 5F is the value of the $5 bills. And if every T is worth 10, then 10T is the value of the $10 bills. So I would just encourage you to spend more time than you think you should at this level before you really even get into doing computation. So what we've done here is we've defined variables and then written our two equations. Okay, so now we are going to first try to solve this by graphing. So start with the coordinate grid, and then what I'm going to do is just zoom in though, because I know we're talking about bills that I can see in front of me, things that I can count. So everything is happening here in quadrant 1. And the two groups of things that we're measuring, as we've already talked about, are the number of $5 bills and the number of $10 bills. And again, this is another place your students could organize it differently, right? They could switch what's on the X and Y axis. And then that's another great opportunity to talk about what's going to happen, or to check out, I wonder what happens, and then talk about that as a class. So I just set the scale as counting by tens because I know the number of bills in all is 80, so I know that I'm not going to go beyond that. So I just set the scale as counting by 10 in both directions. Okay, and what we're going to do is work with one equation at a time. And I think it's just good to say that to your students. Like, it's not everything all at once. We're going to do just one at a time. So let's solve this. Let's graph this equation. F plus T equals 80. So I put F along the x-axis and T along the y-axis. So I just made a T chart here. And then what I did, I just invented some, normally those would be the X values. Here they're the F values. I just invented some. So I'm going to ask you all to now find the corresponding T values and type them into the chat box. So for example, I wrote that F equals 0. And so in this case, T must equal 80, right? Because 0 plus 80 makes the full 80. So in the chat box, please, you could write F equals 0, T equals 80. And then could each of you choose another number and then also type in the corresponding T value. Let's see if we can, as a group, kind of come up with these values. Okay, thanks, Carol. And I just want to tell you, the one reason that I'm doing this is how I have found success by, I do this in class. I just point to a different section of the class and say, you all figure it out when F is 35. You all figure it out when F is 70. Because it allows you to move through the problem and not get caught up in and the students don't get caught in like where it takes so long to get through one problem, and it really motivates people to work together. Okay, so there are the corresponding values. Oh, and you found your own. That's awesome. So we have F values, we have T values, and I just wrote them now as coordinate pairs. And let's graph these points. So 1, 0.2, 3, 4. So graph the points, and there's our line. So this line represents all the possible combinations of $5 and $10 bills to result in 80. And then we would just go through the same process then for the second equation. So I think you all seem to really get this idea, so I'll just click through this one a little more quickly. So again, I invented some F values, and then I substitute those values, or hopefully your students then would substitute those values into the equation, and then solve for T. So you can find the corresponding T values, and then you have created coordinate pairs, and now we can graph those. So here are the points, 1, 2, 3, and 4. And so there's that line. And so what I see is we've graphed these two equations, and I see that they cross. And so then that's the solution. That is, though there are many solutions if you only have a one equation, when working with both equations, there's only one solution that works for both. And that's right where they cross. It's where the F is 60 and the T is 20. So then contextualizing and decontextualizing, the class has 60 $5 bills and 20 $10 bills. And then I would just, we've just been so abstract I would just, with your class, go back and say, okay, what is this happening in real life again? Check it. So yes, 60 and 20 really does make 80 bills. And then $65 bills, that's your 300. 20 $10 bills, that's your 200. So then altogether, that really does make your 500. So graphing is one way to find a solution for a system of equations.
All right, now we're going to approach second method. Graphing is great. We don't always have access to graph paper. Sometimes the numbers aren't super friendly. So we're going to look at the substitution method, and I'm going to revisit that idea of the equal sign and really focus on how two things cannot look the same, but they have equal value. And if they have an equal value, then we can use one to replace for the other one. So that's where the idea of the equal sign is super important, having our students having that solid understanding. So substitution is something we do all the time. We can replace equivalent values, for example, with fractions. If we want to add 1/2 to 1/4, we can't, because in math we can only add the same size measurement to another same size measurement. So, but knowing that 1/2 is the same thing as 2/4, we can substitute them and say, well, 2/4 plus 1/4 is 3/4. So we simply replaced 1/2 with an equivalent value of 2/4. We do it frequently in formulas. Here's an example in geometry. We know the formula is area's length times width. Here's a rectangular shape where our length is 8 meters and our width is 4 meters. And so we can replace the L with the value of 8 and the W with the value of 4 because they are equivalent, do our computation, and find out that the area of this rectangle is 32 meters squared. So once again, it's this idea of replacing equivalent values. So taking the exact same story problem that Amy just did, we're going to look at this system of equations. We have two equations. So we have each equation has an infinite number of solutions, and like she said, we're looking for the one ordered pair that they share. And so we're going to have a strategy of choosing one equation to start with and solving it for a variable. We can pick either one. It doesn't matter, our answer will be the same. And once we do that, we're going to substitute that value into the other equation. So let's start with the first equation. F plus T is equal to 80. I'm going to choose that one because it seems a little bit easier, perhaps. I'm going to solve for T. I'm going to subtract F from both sides, and I get the equation T is equal to 80 minus F. This is something that our students struggle with, is the idea of 80 minus F being a number, but keeping working with them makes it a little easier. This equation tells us that the T value is exactly the same as the number 80 minus F. So now I can use that to go back into my other equation, not the same one I just used, and replace it. So we're going to take the second equation, 5F plus 10T is equal to 500, and replace the T with the equivalent value, 80 minus F. Once I've gotten through this step, I always tell my students, just take a breath. We're just doing straight up first degree algebra. Everything down from here is old, prior knowledge, we can do this. So we're going to use the distributive property, distribute our product of 10, and we're going to simplify, combining 10 times 80 is 800. Now we want to combine like terms. We have the 5F and the negative 10F. Is negative 5F plus 800 equals 500. Continuing down with our algebraic steps, we're going to subtract 800 from both sides. We end up with negative F is equal to negative 300. Divide both sides by negative 5, we get F is equal to 60. So now we know that we have one numerical value for a variable. We have our one of our coordinates. We can simply substitute that 60 into either equation because this is the ordered pair that they share. So once again, we can pick the easier one, but either equation will work. I'm going to replace my F with 60 and then solve for T. So now I have found that F is equal to 60 and my T is equal to 20. And remembering, of course, that this was a story problem to begin with, I need a full solution that we needed 60 $5 bills and 20 $10 bills. going through the process with the students, it's important to always remind them, like I particularly solved for T, but we could have just as easily solved for F. So their choices are really multiple. So as going through the substitution method, are there other things that you've seen with your students that would be important to remind them of or work with? So feel free to chat in the chat box. Again, being a small group, I thought it'd be great to take a quick minute to just see if there were questions about the substitution method or combining this way. Yeah, the work looks really long right here, but you're right, Amy, making sure the little steps are important. Putting in the same value. Can you say more, Andy? Right, yes. Like my students struggled often with 80 minus F being a number, and that's something that is a new idea. We talked about this even today, that you can have a number that doesn't always look like a number, but 80 minus F as an equivalent value can be substituted. All right, Amy, we've got one more method.
Okay, thanks, Rebecca. So now I'm going to move on to another algebraic method that is called elimination, or the combination method. And I was thinking too, how a question that a student may ask is how do you decide which of the algebraic methods to use? And I think with practice and with experience, then some equations just kind of lend themselves to choosing one method, because then it seems easier. That's how I would approach that. Okay, so now we have back to our original two equations. And as I look at these, so I'm a GED student, I'm looking at these and thinking, I need to solve this equation, but the thing that is a problem for me is I'm used to one letter. I'm used to one variable and then everything else being numbers. And so if I need to use everything I know about solving equations, then I need to do something to make sure that I only have, that I just have one variable. And so, that's why this is called elimination. So to me, I found that it was really helpful to share this goal with students. So what we're trying to do here, because we start getting into all these steps, but really what we're trying to do is we're going to combine these two equations so that one of the variables is gone. Because if it was just an F, we would know how to solve it. If it was just a T, we would know how to solve it. So we want one of the variables, we want it to combine to make 0. And so the equation I'm working with is that first one, just because it's simpler. And I'm deciding that I'm going to make the F disappear, or combine to make 0. And so in order to do that, I need to take that F and somehow make it into a negative 5F, because that negative 5F will combine with that positive 5F to be 0. And again, students could make different choices here, and that would be an awesome opportunity for them to have to then kind of defend why they're doing it that way, and have people work through multiple methods and then compare answers at the end. So I am multiplying each side of the first equation by negative 5. And then let's just go through the steps. So I'll distribute that negative 5. And now I've changed, and I'll simplify that equation into negative 5F minus 5T equals negative 400. So now I've got that negative 5F that I was looking for out of the original equation. So just to make this very clean and understandable, we'll copy that first equation, and now we need to bring in that second equation. So I'm taking a version of the first equation, I'm combining it with the second equation just as it is, Now I'm going to combine, and I see that negative 5f combined with 5f, that truly does make 0. So that's gone, and that was what I wanted. And then I will combine the negative 5t with the 10t, and that will result in 5t, and then equals, and then my negative 400 combined with a 500 will make 100. So now I've taken these two equations with two variables, and I've made one equation with one variable, and so then as a math student, that's something that I can work with. So then I just divide and find that t is 20. So then now that I have already solved for t, I can just go back and use substitution and plug that t back into the first equation just because it's easier, but it could be either one. And then I find t is 20, f is 60. So once again, the class had 60 $5 bills and 20 $10 bills. So that's just one more algebraic method for solving a system of equations. So this is where I'm especially interested in input from everyone. As we just talk about the approaching systems of equations in your classes, I just wanted to offer these strategies that I have found helpful. And I'm going to ask you all to raise your hands and also share, especially the people that have just taught this recently. I'm sure things have come up. So when approaching systems of equations, I have found it very helpful or essential to make sure that your students are practicing identifying two equation word problems. Like all that time we spent when I first showed the problem. Make sure to spend all that time and really check yourself as a teacher, and don't jump in and say, and don't help your students with this. Don't say, oh, this is two equations. Have them gain the skills to find that, to discover that, and so you'll have to give them opportunities to practice. Maybe just show them 3 word problems and say which would be which of these could be easily solved by a system of equations, and then why, right? So give them practice with that. Also, of course, always ask open-ended questions, because there are so many places in systems of equations where your students will have to make decisions and then move forward. And there's also more than one correct way to do it. So ask a lot of open-ended questions, and again, hold back from trying to help them by telling them what that next step is. My other thought is that idea of working as a class. It was just really fun when I would assign the X values to just very informally to different groups, and then each group would find the corresponding Y value. It just made us build that graph all together as a group, and then it didn't feel like it took so long to go through all of that, all of those steps. And then also just start small. So just like at the beginning of this section, how I just said, where do these lines cross? What is the solution to both of these lines? You can start there, and so be willing to find ways to start small with your students. So I really want to unmute some people right now and hear some other ideas. I know that some people will have something to say about this. So my question is, what other teaching strategies could you share about teaching systems of equations? So I see Andy has his hand raised. Let's unmute him first. Go ahead, Andy. Thanks.
Okay, can you hear me?
Yes.
Can you hear me? Okay, good.
Yes.
Just a thing, I love the ones you have up here, and the way you guys set it up with the F and T. It's really common for students to absolutely desperately want to use X and Y, just because it's been beat into them. And then some of the questions on the GED sample problems will say something like, let ln be X. And it's like, well, if it's ln, let her be E, because I'll remember that it's ln. So reminding the students that they don't have to use whatever variable the test is asking them to use, because any variable that they use will work. You can figure out the values and then put them back into whatever system the test asked you for to start with. The second one is that quite often in the sample materials in Kaplan or in Steck-Bond, they'll do a lot of two-equation word problems as one-equation problems. Those kind of jump over the first step, and helping your students to see that they're really a two-equation problem can get them into this system of solving that's maybe not quite as confusing. So
Hey,
if they
Andy.
have something like, but
What? Sorry to interrupt, but are there specific things
okay.
that you tell them to look for? Is that what you were about to say? What is it that you're asking your students to look for?
Look for the fact that there are more than one unknown that you're trying to solve for.
Okay.
And then relating the unknowns in. And you were talking about, having two equations, and that's really common. But they do have, I know, at least one sample question that talks about, like, Ellen worked twice as much as Kayla, but Amy worked half as much as Ellen did, right? So all of a sudden now there's three variables, but they can still set up the three equations with them and solve them back together. If Ellen worked twice as much as Kayla, then E equals 2K. And if Amy worked half as much as Ellen, then A equals half E, or equals half of 2K. And so get them to see that, you could set up the much more general equations and then put them back in together. Because quite often the thing will say X plus 2X plus X, and they'll never tell you why the 2X is 2X.
Yeah, and I think what another thing that can do is it also just shows how they've already been maybe solving two like systems of equations, but like
right,
you said,
without even knowing it.
Yep, yeah. So then they can get confidence from that, because that sometimes it's not really needed to. People just kind of do that first equation in their mind, and math books sometimes do too. So I think they could get confidence from that.
And then the other thing I put into the chat, that I make an analogy to replacing a car part. When you're doing substitution, you can think, if I have to take an alternator out of a Ford, I can't put a Chevy alternator back in. It's got to be exactly the same one. So when you took out the T, you replaced it with the 80 minus F, which is exactly the same one, because we told them they're equal.
Awesome. Good, thank you. Thanks, Andy. How about who else? I feel like you all have some experience with this, and I just wonder if you have any tips that you could share, or just specific things that you draw your students' attention to. Don't be shy.
This is Rebecca. I'm just going to add one thing that I've been pushing myself to try more, and it's kind of that idea that I put in the slide of the thought bubbles, of getting them to journal or take notes on their thinking process as they're going. And it helps clarify their steps and also gives them a reference point for coming back to. So just, why am I doing this, and what should I remember for next time, kind of a thing.
Yeah, to make that process more transparent and actually, it shows it's actually happening, that you're actually asking yourself, you're teaching them how to become independent learners, and they're actually answering questions and making decisions as they go. Okay, I think let's move on then. It is 4 o'clock. We still have a half hour of guided practice coming up. Andy, thanks for sharing your ideas with us. Okay, so before we start the guided practice, I just want to invite everyone to register for episode 6. This webinar is part of a series, and episode 6 is, I'm excited about it. It's kind of different. Like, it's a little less mathy, I would say. We're going to be talking about differentiating math instruction in a complex classroom. So that's all of our classrooms. And I'm going to actually have a panel that I'm talking with, and we're going to talk about some specific ways to differentiate, because if we are going to reach all students, there has to be some form of differentiating happening. So go to the Atlas website, please sign up for that and bring a friend. And just reminding you again, this is part of a series. All of these are saved on the Minnesota ABE Professional Development YouTube channel now. So, Carol, March 9th is Monday. Is there a mistake with the day of the week?
It says Wednesday.
So whatever, March 9th is the day. So thanks for pointing that out. Whatever is, I'll do any adjustments that I need to make on the Atlas website. So I hope you all can join us for that. And let's go ahead and get into the guided practice. So we have some planned activities for systems of equations and also for inequalities. Before we jump into that, are there any thoughts or questions? Because we have time now.
This is a great time for thoughts, questions, or preferences. We have a few problems we can work through: substitution or elimination method. We've got inequalities. Are there preferences that you would like to see at this point? It's a nice small group. You guys can really help direct what we do from here. Okay.
I can see, Rebecca, everybody is nodding and smiling right now. And they're listening to what you're going to do next, I can tell.
Well, what we have lined up is just more practice of the same. Here is a similar story problem to what Amy chose. Once again, it has to do with money. It's a very common style story problem for this type of thing. I chose this particular one because it has one extra attend to precision issue. So if you want to take a minute to read the story problem and then think about what students need to know and look at what the stumbling block might be for this one. So go ahead and either raise your hand and we can unmute you so you can actually talk, or feel free to chat in the chat box. What are some things you notice about this problem that are going to be important? So Connie, you wrote decimals. Can you say more about the decimals? What were you thinking? Yeah. There is something about the decimals that are a tricky thing. And that's it. Amy mentioned it. It's the dollars versus pennies. We immediately think 25 cents, but then our money is in dollars. And having that piece different can, of course, ruin your answer as far as accuracy. So let's look at this one, much the same as Amy did. And what would be the same information? We've got to come up, we've got unknowns. Like I said, this can be very conversational, so raise your hand or we can talk through it. But what are the two equations that we're looking for this one? There we go. I like that. Quarters plus nickels is 18 would be a good equation. I already typed in here, so of course I have x plus y. So if we want to add up the number of quarters plus the number of dimes, we're going to have something like x plus y is 18, q plus n is 18, however we want that to be. And when we're looking at the total money, this is where I think people get tripped up frequently. We have to decide if we're using 25 cents, so 25, or 25 hundredths, and that has to correspond with our solution. So either we use 25 hundredths x plus 5 hundredths y is $3.10, or turn everything into pennies. So I chose to turn everything into pennies to avoid decimals altogether, but it's a great conversation to have with students about making sure we're using the same unit throughout your problem.
Rebecca,
Yes.
you said this at the beginning, but it's just very glaring to me that if you use 3.10 or 310, it's just it's totally different, right? And so
Right.
I think this would be a way for students to say that they're being careful with their decimal, not because the teacher told them to, but because it has a totally different meaning, and I think that would become that would be really evident in this example.
Well, yes, and another thing I'm trying to really focus my students from day one of the lower level through the last day of the higher level that I teach is that you can only add the same unit to the same unit, and that comes up from taking inventory of adding apples and oranges all the way into calculus, and the idea that x plus y cannot be combined if we're adding, and a fourth and a third cannot be combined unless we trade them in for something else, and a penny and a dollar can't be combined straight up like this. It's just the idea of making sure our units are always the same, so it's good algebraic thinking. So, like I said, if we have these examples set up, we can walk through the substitution method and elimination method again. If someone has suggestions or would like to see something else, please interject. So once again, we've got the two equations. We get to choose what equation to solve for, and of course, ideally, we'll pick the easier one. Here we have that y is equal to negative x plus 18 by solving for y. That equivalent value is going to come up again, so I get to replace all those y's with a negative x plus 18. So I'm going to go through my equation and pull out the y and replace it with negative x plus 18. I didn't go through step by step as slowly this time for the extended review, but all of it is algebraic, distributive property, simply combining like terms, all of those things to simplify down and getting to x is equal to 11. Once we have one variable solved, we can pick any equation to plug it in. And maybe someone wants to chat why. Does it matter if I plug it into x plus y equals 18 or 25x plus 5y equals 310? Does it matter where I plug that in? So the idea is, once again, these are two linear equations, and they each have an infinite number of solutions. I'm looking for the one ordered pair that they share, and I know that both of them are going to share that same x. And that's exactly right, Connie. Thank you. They both have an ordered pair, 11 comma something. So it doesn't matter if I plug that 11 in for x in the first equation or the second equation, because I'm looking for the one ordered pair that they share. I plug it in. I'm going to choose the easier one to save myself some time. I get y is equal to 11, and therefore I know there's 11 quarters and 7 nickels. One thing I found very interesting as I was going through this system was I always thought substitution felt easier in the past, and going through that I realized that actually elimination feels easier than I remembered. So if we want to sneak to the elimination method, I'm going to pick an equation. Once again, it doesn't matter which one, so I'm going to choose the top one because it feels like it's going to be simpler. I'm going to multiply both sides by -5. So then I get -5x plus 5y is equal to -90. And I'm going to add that to my other equation. Like Amy said, this can be tricky for students to understand why we can add equations, but we're following the equal sign. If I have an equation where both sides have the same value, I can add that to another equation where both sides have the same value. As I do that, I will hope to eliminate a variable, get it down to a one variable equation, and I get x is equal to 11. Substituting back in once again, I'll end up with 7, and I have the same solution.
Rebecca, I just want to add something to that. I'm going to go back a slide.
Mm-hmm.
An idea for a just like a way to engage students is either with elimination or with substitution. What you could do is, and because there's so many steps to this algebra, I think it would be pretty interesting to show the problem already worked out, but then come up with a number for x, but make it more than 18, right? So make some kind of a mistake with distributing or something, but where x comes up to be like 20, and then just ask your students, is this right? Why or why not? Can you find the mistake? And because then they can just talk about the mean, like if there are only 18, it has to be less than 18. So there's like that kind of common sense thinking. But then they could also just go back, because it's such dense kind of algebra balancing skills, it would really push them to practice those skills. So I don't know, that just popped into my mind as another extension activity that you could do with this.
No, that would be a great idea. There's certain levels of math that we check out of estimating the answer. We just do the work, we assume it's right, and we don't stop to reflect. So I think that's an excellent idea, Amy.
Thanks. So the next, now we have a little bit of guided practice around inequalities. Do you want to add anything or ask anything else about the systems of equations? You can do that by raising your hand or chatting. I see that Andy has his hand up. While Andy is explaining, you could also chat any other questions or thoughts that you have. Go ahead, Andy.
Okay, and I love the thing of, getting the common sense of, if it's 18, 20 doesn't work. For this one, where we're talking about quarters and nickels, in order for it to come out to be like $3.10, a nice round number, that if the students can make the connection that they have to either both be odd or both be even, you end up with 11 quarters and 7 nickels, but you couldn't have ended up with like 10 quarters and 7 nickels because you wouldn't have had the right numbers to go through. So it's a quick check for them also to think of what the possible values really could be.
And thank you for that, Andy. And you're reminding me, I'm jumping ahead to the next webinar, but about differentiation. So, wouldn't it be awesome if you have a multi-level class? Some of your students could be solving this question by using systems of equations, and then some could be solving this by guess and check, by making a table, by going through the logic that, like Andy was describing. What What are the possibilities here? And I love that there could be a multi-level class all working on the same question and taking different solution pathways. Okay, let's go on, and we'll just do a little bit of interaction around inequalities, just as a quick review for you before we go. So I want you to please chat this answer. This is I take this as a key point. So what is the rule for solving inequalities? They work just like equations, except what? Type that in the chat box. Just as a review, I want to make sure that that is clear to you. Rebecca helped us understand why, but I just want to know the rule. What is the rule for solving inequalities? They work just like equations, except what? Could you type it in? They are not equal. That's true, they're not equal. How about in the steps of solving them? In the steps of solving equations, I do everything exactly the same. I add to both sides or subtract, divide. All that happens step by step. Except, Darlene said it very succinctly, you switch signs when multiplying or dividing by a negative. So just a reminder to flip that sign when you multiply or divide by a negative. I remember the purple algebra book that I used to teach out of. I know Darlene has experience with that book too. I would just have my students highlight that sentence in that book. Okay, so just make sure that you remind your students to watch out for that, the multiplying or dividing by a negative. Thank you for chatting in about that. Okay, so now let's look at this. There's an inequality on the screen. And I'm going to ask you to do a couple things here. And with the idea, you know, you could do this with your students. So given that inequality that's written, I wonder if someone could read it. Just read it out loud and then name 3 example solutions. Name 3 numbers that are not solutions. And then would this be graphed with an open or closed circle? I wonder if someone would be willing to raise their hand and just answer these out loud. So reading this inequality, that's, I bet you all could do that. Who wants to volunteer? Beverly, thank you so much for volunteering. Let me unmute you.
Can you hear me?
Yeah, I can hear you. Go ahead and answer all these, please.
Okay. So X is less than 4.
Yes.
So one example would be 3 is less than 4. 0 is less than 4. And 1 is less than 4.
Great. Keep going.
Then would this be graphed with an open or a closed circle? It would have to have the open circle because 4 is not included.
Correct.
And I lost the visual.
Me too. Rebecca, can you work on that? I agree that.
Sorry, I'm working on it. I just realized I can't hear.
We are back.
Apologies, sorry.
It's okay. Open circle, just like you said. And then.
Oh, I'm sorry. Yes, I missed the name 3 numbers that are not solutions.
Okay. So, what are those?
5, 100, 7.
Awesome.
Nice.
just right. And so, I mean, so as a teacher, as a busy teacher, just writing that on the board and then having these same questions each day. Every student could have their own answers. There's room for creativity. I see some creative answers that are in the chat box. So, and yet there's a lot of rich information right here. So Beverly, thank you so much for your participation.
You're welcome.
Let's see, I think we have one more example. So this, we actually didn't mention this yet, but in the follow-up email, Rebecca and I just included a link to a website that we like that for sample worksheets and with the solutions that for inequalities and also for systems of equations. It's the CUDA software website. So that link will be in your follow-up email, so watch for that. But here I just took this one example. This will be the last sample problem that we do together today. So I see an inequality, negative 2r minus 2 is less than or equal to 4. And then the instructions say, solve the inequality and graph its solution. Just take a minute and do that on your own scratch paper. Start to solve that. Rebecca, what would you do first in this situation? What would be the first algebraic problem-solving step that you would take?
Well,
I'm going to try to read your mind.
I'm having my students remember order of operations.
Okay.
And then to solve, you have to go backwards through order of operations.
Okay.
So what's happening to your variable? It's multiplied by negative 2, and after that we subtract 2. So we need to undo the last thing, so we need to undo subtraction of 2. So we need to add 2 to both sides.
Awesome, thank you. So we add 2 to both sides, and then one more step is what?
Yep. Undo the multiplication by doing what? Go ahead, sorry.
So undoing multiplication is division, and then it lights up in my mind, oh, we're dividing by negative. So I better reverse the sign. And like you all have brought up, you also could now check these answers back in the original equation to see if it makes sense. So now we have solved the inequality, and this is what the answer looks like on the worksheet. And I see that this circle is filled in because it's not just greater than, it's greater than or also equal to negative 3. So there will be more samples of these in your follow-up email. Okay, and I believe that is, oh, what a nice ending. I believe that's all. That is all that we have for today. So thank you so much for your participation. Hope to see you for the next Equip episode, and send your friends to the recording of this Equip episode that you'll be able to find on the YouTube channel. So thanks again, everybody, and I hope that you have a great evening.
Thanks so much for your participation, guys. Thank you.